Let's review a few things about classical probability. In classical probability, the probability of an event is equal to the number of favorable outcomes divided by the total number of possible outcomes. The key point in classical probability is that we are able to count the number of favorable outcomes and also count the total number of possible outcomes. Consider an experiment of rolling a 6-sided die. What is the probability of the event an even number of spots appear face up? Here are the total number of outcomes of throwing a dice. You can throw a 1, a 2, a 3, a 4, a 5, or a 6, right? Of these, there are 3 favorable outcomes, a 2, a 4, and a 6, in the collection of 6 equally likely possible outcomes. If we were to approach this problem from an empirical probability perspective, we would throw this dice, maybe 1,000 times, and then see what the proportion of an even event occurs. But with the throw of a dice, there's no reason to have to do this kind of experiment, because by being able to count the number of favorable outcomes and counting the total number of outcomes, the probability of this event is simply the total number of favorable outcomes, which is 3, divided by the total number of possible outcomes, which is 6. The key difference here, once again, is the ability for us to count the number of favorable outcomes and the total number of possible outcomes. In some situations that we know about, counting is pretty straightforward. For example, with this dice, we know that there are only 6 possible outcomes. Sometimes with other experiments, it is also easy to count up the total number of outcomes. For example, if we toss a coin, we know that the total number of outcomes is 2, a head or a tail. But how about if we were trying to count up the number of ways that Dell computer can configure its laptop? Wow, maybe 1,000,000 or something like that. Counting becomes a little bit more difficult. However, let's learn about some general rules of counting that will help us do these calculations. By the way, even with classical probability, randomness still exists. Suppose we toss a fair coin. The result of each toss is either a head or a tail. If we toss the coin a great number of times, the probability of the outcomes of heads will approach 0.5. The following table reports the result of an experiment of flipping a fair coin 1, 10, 50, 100, 500, 1,000, and 10,000 times, and then computes the relative frequency of heads. Notice that it approaches 0.5. As you might see, since we know something about this experiment, we don't have to toss a coin 1,000 times to know that the probability of a head is 0.5. That's what we can calculate using the classical probability approach. For classical probability, we need to count the total number of outcomes. Let's learn about 3 ways of counting. They are arrangements, permutations, and combinations. Let's look at this arrangement example. An automobile dealer wants to advertise that for $29,999 you can buy a convertible, a 2-door sedan, or a 4-door model with your choice of either wire wheel covers or solid wheel covers. How many different arrangements of models and wheel covers can the dealer offer? For arrangements, we can use the multiplication formula, which is simply the product of m times n, where m is the number of models and n is the number of wheel cover types. In our problem, we have 3 models and 2 wheel cover types. We multiply 3 by 2 and get 6. This doesn't seem that difficult. Let's take another example. Consider that you want to buy a laptop from the Dell website. How many different models of the Inspiron laptop can Dell advertise? To answer this question, we would have to know how many different versions of each option Dell provides. In a very simple scenario, if we had 4 hard disk types and 3 monitors, and let's say 2 different memory configurations, to figure out the total number of models, we would take 4 times 3 times 2, which is 24. Let's take another example, rolling 2 dice. What are all the outcomes, and then what is the probability of rolling a 5 or a 7? Let's think about this a little bit. The first dice has 6 different possibilities. Also, the second dice has the same thing, 6. So the total number of outcomes is 6 times 6, or 36. In order to calculate the probability of tossing a 5, we need to know how many different ways we can throw a 5. We can use this probability distribution for the result of throwing 2 dice to see that there are 4 different ways of throwing a 5. Using the classical probability approach, the probability of throwing a 5 is 4 divided by 36, which is 11.1%. Even though we know something about this experiment, the calculations become a little bit more difficult, don't they? Calculating the number of arrangements might seem pretty easy, especially when we have distinctly different components. But sometimes it is a little bit more complex. Let me give you an example. Consider that we want to paint a room that has 4 walls. Also consider that we have 4 different colors of paint. How many different ways can we paint this room? Using the same approach that we took for the car and our laptop, we can multiply 4 colors on the first wall times 4 on the second times 4 on the third times 4 on the fourth and come up with 256 different ways. How would this differ if we had 6 colors of paint? Well, it is simply 6 times 6 times 6 times 6, or 1,296. Now let's create a slightly different question about painting a room with 4 different colors. How about if I ask the question this way? How many different ways can we paint a room with 4 colors of paint where when we use one color for one wall, we cannot use it again on another wall? This question, if you think about it a little bit, is very similar to calculating arrangements. We have 4 colors for the first wall. When we use that first color, we can't use it on the second wall. So we only have 3 colors available for the second, then 2 for the third, and then 1 for the last wall. So the calculation would be 4 times 3 times 2 times 1, or 24. Let me ask another question that is very similar to this. If I had, let's say 12 different colors of paint, and I wanted to paint 12 different walls, how many different ways could I paint them? Well, using the same approach, it would be 12 times 11 times 10 times 9 times 8 times and so forth, down to 1. This kind of calculation becomes a little bit more cumbersome, but if you remember back to mathematics, when we have this kind of scenario, it is called factorial and is denoted by n exclamation. There is an equation to determine n factorial. But if we had to do this calculation frequently, we might want to buy a calculator, and maybe some of you already have this kind of calculator, with a n factorial key on the keyboard. Calculating 12 factorial would be pretty simple. You just enter 12 and then hit the special key, and the calculation is immediately done for you. Well, guess what? Microsoft Excel can also do this factorial calculation. This n factorial becomes another way of counting. Let's return to our painting a room problem and look at this second question. How would our answer differ if we had 6 colors of paint to paint 4 walls? You might want to quickly blurt out 6 factorial, but this is not correct. Consider what happens. You have 6 colors for the first wall, times 5 for the second, times 4 for the third, times 3 for the fourth. You don't multiply this times the 2 times the 1. So for this problem, we cannot use our n factorial equation. But there is another way that we can do this calculation very quickly. This type of problem can be solved with the permutation formula shown on this PowerPoint. A permutation is the number of ways to choose R objects from a group of N objects, where the order of arrangements is important. We'll talk a little bit more about this order in just a moment. In our problem of painting the room, we are going to choose 4 colors from a group of 6 possible colors. To do this kind of calculation, however, you probably need a special calculator that was designed for statistics. It might have a permutation button built into it. Guess what? Microsoft Excel also has a permutation function. This is how we are going to do this calculation. There's one more scenario that might occur when we're painting our room with these 6 different colors. Consider that we paint a room with the 4 following colors: blue, red, yellow, and green, using the blue on the first wall, red on the second, yellow on the third, and green on the fourth wall. Somebody else chooses the same 4 colors but uses blue on the second wall, not the first, and then proceeds painting the other 3 walls with the same red, yellow, and green colors. What might happen when somebody walks into either of these 2 rooms? Somebody might look at this and say, hey, they're the same. Both use blue, red, yellow, and green, and I don't see any difference about starting on the first wall versus the second wall. I only want to count these as one way of painting the room. This becomes a slightly different problem. The question is, how many ways can we pick 4 colors from a total of 6? One way that we have already seen is called a permutation, where the order is important, meaning that the 4 colors, blue, red, yellow, and green, are different depending upon which wall we begin with. Order is important. The other scenario is where order is not important and we don't want to double count. This is referred to as a combination. And if you think of our problem of painting the walls, combinations are always less than permutations. I'd like to think of this as P is always greater than or equal to C. We still have to do the calculation, but guess what? There is a formula for combinations. Here it is shown on this PowerPoint. In words, a combination is the number of ways to choose R objects from a group of N objects without regard to order. In other words, if we had the letters ABC and rearranged them to CBA, they would not be counted as different. CBA and ABC are the same 3 letters. Order is not important. Sometimes it will be obvious when to use a permutation instead of a combination or vice versa. However, sometimes it's going to take some hard thinking as to whether or not order is or isn't important when you count up the different ways of doing something. Let's look at a couple examples. There are 12 players on the Carolina Forest High School basketball team. Coach Thompson must pick 5 players among the 12 on the team to comprise the starting lineup. How many different groups are possible? Well, is this a combination or a permutation? When you consider picking the 5 people, it doesn't matter who is first in line, second in line, and so forth. They could even mix up. It doesn't matter. Order is not important. So this is a combination. Using the equation, we calculate 792 different ways of picking 5 players from a group of 12. Here's another problem. Suppose that in addition to selecting the group, the coach must also rank each of the players in that starting lineup according to their ability. Well, when you think about this, of the 5 players, one of them could be ranked number 1, or that person could be ranked number 2 or number 3. This problem is where order is important, and therefore it's a permutation. Look at this. There are 95,040 ways of picking the 5 and ranking them, or in other words, ordering them. Wow, these calculations can become a bit difficult. This is why we are going to use Microsoft Excel to count, or in other words, to calculate combinations and permutations. I can't wait. Thanks for taking some time to spend some moments with me. I hope you have enjoyed what I have shared with you. If you ever have any questions or comments, please visit my website or email me. I hope that you can join me again soon. Bye-bye.